Okay, so this is part two of the lecture on chapter two of the base book. I'm going to pull up my slides so that you can see them. So we stopped at the point where I had illustrated the use of the beta binomial conjugate case, and what we saw was an example of how this equation Bayes rule up to proportionality, that is equation 22, can be used in practice to arrive at a posterior distribution for a parameter of interest given some likelihood and some prior. So the case that we saw was binomial likelihood, beta prior on the theta parameter. And what this does is it gives us a posterior distribution that's also a beta distribution, but with updated parameters A and B. So we are learning from data in a sense, right? Now, in this simple example and the next example that I'll show you, we are only talking about a single parameter in the model. But later on, we will work with models with dozens or maybe hundreds of parameters, right? So, but the equation is not going to change. Instead of theta being a single parameter, it's going to be a vector of parameters. So let's turn to the second example, which is somewhat, um, it looks somewhat more complex, but it's actually just as easy as the beta binomial. This is the Poisson gamma case. So the situation that we want to imagine is that, let's say that we are doing an eye tracking study and we are counting the total number of leftward eye movements per word in the study. So this is actual data from a 2011 paper that we had published. So I just extracted from the paper, from one of the experiments, I just extracted some data where from multiple subjects who are seeing multiple items in different conditions, what we are recording is the total regression count. That means the total number of leftward eye movements per word while they're reading the sentence. So it can happen, when you're reading a sentence. When we do eye tracking studies, what we do is we are recording the eye movements, and so we know with a device called an eye tracker. And so what we know when subjects are reading the sentences on the screen, we know which word they're looking at and how long they look at it. So this information is recorded in a text file, and so what we end up with is the ability to look at the history of the eye movements. So these are words that people are reading, just using the dashes to stand in for words. Typically, when the eyes move, you might fixate at a particular point in the word, you might fixate again at that word, and then you might move on to the next word, or you might even skip one word and move on to the next word. And then it can happen that you move leftwards. And these regressions are theoretically interesting for various reasons. So they sometimes signal increased processing difficulty. So they can index increased, parsing difficulty or something like that. So that's why we're interested in these counts, but these are discrete counts, right? So you can have zero regressions, one, two, three, four, or whatever, but you can't have 2.5 regressions, from a word. So this is a discrete value, but it's not like the 0, 1 responses in the binomial, right? So the Poisson distribution is a good distribution for modeling this kind of data. And if you look at the data itself, this is the actual data that from the paper. What we notice is that the distribution of counts it can be very large. This is probably at the end of the sentence. Sometimes people run into difficulty at the end of the sentence and they make a lot of regressions to try to recover if they have difficulty. But you see that the average number of regressions is 1.1. So I mean, don't be confused that this is now a continuous value. This is the average of a bunch of discrete values, right? That's why um, it's 1.165. But you can see that the median is about 1, and there's not a very large number of regressions in most cases. This is just missing data. And so in some rare cases, they might have done a lot of regressions. So this kind of data can be modeled with a Poisson distribution, right? So This is what a Poisson distribution looks like. The number of times that the regressions occurred from word can be modeled using the Poisson. So the number of regressions is this x here. And the Poisson distribution has a parameter lambda, just like the binomial has the theta parameter. The Poisson has a rate parameter which determines how large the mean is and so on, right? So what we have is the definition of the Poisson distribution in equation 23. And lambda, of course, is going to have to be greater than 0, but it's an unknown parameter and we have to estimate it from the data. The x's, the observed values, will be 0 or larger than 0, and they can't be negative, right? Those are the counts. Okay, so yeah, so we are also assuming that the data points that we have, the number of regressions that we're observing, they're independent of each other, given lambda, given the rate parameter, all these values I assume to be independent in the discussion that I'm presenting today. Of course, we know that this is technically not correct for these particular data because we're getting multiple data points from the same subject. So obviously these values are not independent of each other, right? But I'm ignoring that detail for now. Okay, so I'm just going to assume that they're independent for simplicity. And so we can generate such independent data using the DPQR, the R Poisson function from the DPQR family. And so I'm just generating 10 simulated data points from a Poisson distribution with lambda equal to 3. So the average the average count for these simulated data is 3. But you can see that there's some random variability here. Okay. So that's how we would generate simulated data with the Poisson. And you can visualize that for lambda equal to 3. This is what it looks like. So now let's think about a concrete situation that we are going to address. We want to estimate, we want to figure out the posterior distribution of the lambda parameter in the Poisson distribution given the data, right? That's what Bayes rule is for, right? So what's missing right now is some kind of prior on the lambda parameter. So we have to figure out a prior that we can use for our lambda parameter, which is the rate parameter. So it turns out that one possible choice that we could make is to choose the gamma distribution for the lambda parameter. Later on, you will see that you could choose a whole array of alternative distributions as a prior, depending for lambda, depending on what you think is a reasonable prior. But right now, for convenience, we are choosing the gamma distribution as a prior for lambda. And the gamma distribution also takes two parameters, A and B. These are called shape and rate parameters, and they determine the shape of the probability density function. Okay. So let's say that the starting point of our research is that we have some data, okay, which can be assumed to be coming from the Poisson distribution. And we know that we are going to define a prior for the lambda parameter, but we don't know what values to give to the A and B parameters of the gamma distribution such that we have the appropriate shape, right? But we know one detail from previous research. The detail that we know from previous research that we know is that the mean for lambda is 3 and the variance for lambda is 1.5. This could have been derived from previous research, right? So we could have seen a previously published paper or seen a meta-analysis or something that gives us um, estimates of the mean of lambda and the variance of lambda. We know these two pieces of information, okay? We are going to use these two pieces of information, the mean and the variance, to figure out what values of A and B, the shape and rate parameters we should use in the gamma distribution to specify the prior on lambda. Okay, so that's what the next step will be. So first of all, the gamma distribution looks like this. As I said, it's parameterized by two numerical values, A and B, and the probability density function is given here. So you can take a look at this in your own time. It's nothing special here, but what I want to show you is that you can get a handle on what this distribution looks like by using the R gamma function for generating random data. So here I'm generating 10 random data points from just an arbitrary gamma distribution, just because I wanted to show what it looks like with shape 3 and rate 1. So A and B parameters are 3 and 1. And so you see, the kind of continuous values that the gamma distribution will produce. So the gamma distribution is a continuous distribution. The Poisson distribution is not. It's a discrete distribution, right? But we are modeling the prior on the lambda parameter. And so we are using a continuous distribution, the gamma distribution, to model that. And so the rate value can be, any real number. So it doesn't have to be a discrete number. That's why we are getting these kinds of, numbers out of this gamma distribution because it's a continuous distribution. So here's the visualization of the gamma PDF for A equal to 3, B equal to 1. And you can see that it peaks around here, around 2 or so. And it's got a long tail to the right, right? So this could represent, your belief about plausible values of the lambda parameter for the total regression counts that we are trying to model, right? So this may not be a crazy prior distribution, actually. Even this, without knowing anything else about the problem, even this could be a reasonable prior distribution because we know from at least we do know that regressions don't don't have a very high count, right? So normally you have 2 to 3 regressions in most cases at most, So this would not be a wild prior distribution. But we're going to do it in a more principled way. What we are going to do is we're going to say that yes, we're going to define a gamma prior on the lambda parameter, but we have to have a more principled way to decide on the A and B parameters. So we're going to use the information that we already have from previous research. We know that the lambda parameter has a certain mean and a certain variance. One thing that one fact about the gamma PDF is that the mean of the gamma PDF is A divided by B. So A and B are the two parameters here, and the variance is A over B squared. So if you know the mean and the variance from previous research, you can equate it to these variables and then solve for A and B. Two variables, two equations, you can do this, right? No problem. So let's do that. We know that the mean and variance from lambda is 3 and 1.5 respectively. So, and we also know the formulas for mean and variance in the gamma. So we're going to solve for A and B, right? So that's pretty easy. So here I'm solving for A and B. If you do the math now, I'll leave you to work this out. The result is that A is 6 and B is 2. Okay, so now we know what the prior should be based on prior knowledge about lambda, right? So this is an example of how you would come up with a more principled way to decide on what the prior distribution should be for the lambda parameter. So this is what the lambda parameter looks like. It doesn't look very different from 3.1. You see that here? It's slightly different, but it's not dramatically different. So actually both of those priors would not be crazy priors, right? I mean, it's pretty likely that I've forgotten, why I chose 3 and 1 here, but most likely I was trying to choose some reasonable, parameters for the gamma distribution so that I get a reasonable prior distribution on lambda based on just what I know about eye tracking and regressions, right? But this is what we come up with in a more principled way. So now we have a good reason to justify why we are choosing this prior for lambda. It's based on prior work. Okay. So now I have the prior. And, if you don't believe, maybe sometimes, you're doing simple algebra, you make a mistake. Okay. It can happen to anyone. And so, what I would do, if I feel uncertain about solving such an equation, did I really get it right? What I would do is I would try to cross check by uh, trying to get to the same result using a different method. So one easy way to check whether, you know, if you set the shape and rate parameters to 6 and 2, is the mean and variance actually 3 and 1.5? You can check that by just doing some Monte Carlo simulations. Just generate 10,000 simulated data points from a gamma distribution with shape 6, rate 2, and then compute the mean and the variance. And as you can see here, it seems that my calculations were correct because I'm getting a mean of 3 and a variance of 1.5. So that's just a cross check, just a sanity check to make sure I didn't mess up something. Okay. It's a good exercise to do that kind of thing, to just solve the same problem in two different ways to make sure that you're getting the same answer. Okay. All right, so now we are back in business. We want to derive the posterior by multiplying the likelihood with the prior, right? So we know what the likelihood is. It's a Poisson. We are assuming n independent data points, right? And we're going to multiply this Poisson likelihood with the prior. So now one thing to notice is that what I'm doing here is that because I have n independent data points, right? I just want you to I want to make sure that you're able to follow this story, right? So um, if I have n independent data points, right? So it's my data is actually a vector of n counts, right? Sorry, n counts, right? So each of these data points is coming from a Poisson distribution. So the first data point, which I'm calling x sub 1, right, is coming from um, the uh, is coming from this Poisson distribution with um, lambda to the power of x1, right? And divided by x1 factorial, right? That's the density of the first data point. What's the density of the second data point? X2, right? X sub 2. So, so the density of the second data point would be exactly the same, except instead of writing lambda x1, I would write lambda x2, and in the denominator, I will also have x2 factorial, right? So if I had only two data points, imagine that I had only two data points, x1 and x2. So what would be the um, joint density or joint probability in this case, because this is a discrete distribution, right? What would be the joint probability of these two independent data points? It would be the product of these two. Remember, in a discrete distribution, this is the probability of getting x1. This is the probability of getting x2 because it's discrete, right? So if you want to multiply it, we're going to get the joint probability of these two, observing these two numbers, right? So we are answering the question, what's the probability of observing x1 and x2, right? That's what we are figuring out. And that would be the product of these two things. Now, if I had only two data points and I was multiplying these two terms, what would I end up with, right? What I would end up with is exponential minus lambda times exponential minus lambda, right? These two terms, right? They're, what am I doing here? I'm losing my mind, right? Let me start over, sorry. First of all, what I wanted to show you is that if I wanted to multiply these two terms, one thing important that will happen is that I'm going to get x1 plus x2, right? And what will happen here is that I'm going to be multiplying these two guys, right? So let's see what this looks like, okay? So it will be exponential minus lambda times exponential minus lambda, right? That's what would happen here. And so what would this simplify to? Right? So the exponential, I'm writing it in, in this mathematical form, which is easier to read, but this is also an exponent. So really what we're doing is, right, what will happen here is that I'm going to have to add the exponents, right? So it's going to have to be exponent minus lambda minus lambda, right? Which will be exponent minus 2 lambda, right? So that's the case for two data points. Now, if I had n data points, right? If I had, let's say, 10 data points, then it would not be 2 here. It would be n or 10 or whatever the number is, number of data points is, right? And so that's why what you're looking at on the right-hand side of the screen is the situation where we have x1 to xn data points, independent data points. And what we are doing is we are multiplying the probability of observing x1, x2, all the way to xn. And that's what you're seeing in the very first line here, which says exponent, what was it? Minus lambda x1 over x1 factorial times exponent. Oh, you can't see anything, can you? Sorry. Just move this over. Um, Minus lambda x2, x2 factorial, etc., all the way, right? That's what we are seeing over here, right? And so now we can simplify this a little bit by this, instead of writing this multiplication sign, I'm just writing the product. Okay, so the product goes from 1 to n. And so instead of writing x1, x2 to xn, I'm writing x sub I, right? So I've just converted this long term of n data, the probabilities, joint probabilities of n data points here into one compact expression by using this product, this sign for the product. So instead of using these product signs, and I'm using, instead of x1, x2, x3, x4, xn, I'm using x sub I now, right? So I've just made it more compact. And so this is just like the summation sign, except it's for products, okay? And so just as I showed you for two data points, I had to sum up the exponents, you remember? Right? I had to sum these two guys up for two data points. And here I ended up with minus 2 lambda n because I had two data points. Similarly, if I have n data points, I'm going to end up with exponent minus n lambda. And then the sum of all the n data points will be in the exponent for lambda, right? So that's how I end up with this term here. And of course, the denominator is x1 factorial multiplied with x2 factorial multiplied with x3 factorial all the way up to x10 factorial or xn factorial, sorry. So that's just the product term in the denominator here. So that's how I end up with this funny looking expression, which represents the joint, um, this represents the joint likelihood that we are going to plug into the into Bayes' rule to get the posterior for lambda. Right? This is the joint likelihood for all the data that we have observed, all the independent data we have observed. Okay, so now computing the posterior is going to be super easy, right? Because all we have to do is we take this term that I just developed for the n data points and we multiply it with the gamma prior. This is the PDF of the gamma. Now, one thing to notice in this equation, which looks horribly complicated, equation 30, is that certain terms in this equation are actually constants. And in fact, they together constitute the normalizing constant, right? So remember that when we define the prior for lambda, we specify some values, some constant values for a and b. So b to the power of a is a constant. Gamma a is also a constant, okay? And the data have been observed, right? Those are fixed numbers. So this is also a constant. So what we end up with is that these terms, this denominator here, this denominator here, and b to the power of a, these terms do not involve lambda at all, and they are actually the make up the normalizing constant here for the posterior. So what we're going to do is we're going to drop those because lambda is not involved anyway in any of these. And we can always figure out the normalizing constant once we get to the posterior. We can't always do that, but in this particular case, we can. Okay. And so we're going to only look at the kernel of the likelihood and the kernel of the prior because that's where the lambda turns up, right? That's where we see the lambda term. So, so what we're going to do with these kernels is that we're going to compute the posterior up to proportionality, right? So how do we do that? Let's do this, okay? This looks hard, but actually it's pretty simple. You'll be surprised, okay? So I'm going to pull this here, put this here so I can write on the left-hand side. All right, so here we go, okay? So I've got the kernel of the Poisson likelihood minus n lambda, right? And then I've got lambda to the and summation of x, right? That's my likelihood. And let me make some more space here. And I'm going to now write only the kernel of the gamma, right? And the kernel of the gamma is lambda a minus 1. I have chosen a and b. A was 6 and b was 2 or something like that. But I'm just taking the most general case here that I've chosen some a and some b. Okay? And so exponent minus b lambda. So these are my likelihood and prior terms, right? So what's going to happen next? So notice that I've got an exponential term here, exponential term here. So I can put those guys together. And I've got a lambda term here and a lambda term here. So I can put those guys together, right? So let's do that. So what's going to happen is that I'm going to go to the exponent minus n lambda. And let me put the exponents together, right? So exponent minus b lambda, right? And I'll put the lambdas together now so that I can add them up. Sum of x times lambda a minus 1, right? This one is easy, okay? Because now I can just simplify this to sum of x plus a minus 1, right? And this one, how do I simplify this one, right? So this one requires a little bit more work because I've got minus n lambda minus b lambda. So I'm adding up the exponents like before. And if I wanted to, I could simplify this a little bit because I see that lambda is a common term here. And so I could write that as exponent um, minus lambda. And then I would write n plus b because minus plus gives me a minus. So if I open up the brackets, I would again end up with minus n lambda minus b lambda, right? So that's why I've written it minus lambda um, n plus b in brackets. Okay, so what I end up with is this expression, sum of x plus a minus 1. And what's interesting about this expression is that it looks exactly like the kernel of a gamma distribution, right? So what's going on here? So look, if I were to lump these guys together, right? And if I were to call, if I were to call this A star, okay? And if I were to call this B star, then oh, sorry, you can't see this. I'm so sorry. It's not good. Okay, so uh, I hope that this was clear. So what I just did was that I just simplified these terms until I ended up with this expression here, right? And so what I'm trying to say is that once I multiply those the likelihood and the prior, I end up with, just want to make sure that you can see this, minus lambda n plus b, and this n plus b is my updated b in the posterior. So I'm going to call it b star, and my lambda here, lambda has an updated a, which is my A star, which is the new A and B parameters of my posterior distribution for lambda, given the data that I have. So what I've done is I've learned from the data. Here's the data coming in. Here's the data coming in, right? The sample size and the actual counts are coming into the analysis to give us updated parameters for the gamma distribution that represents the posterior distribution of the lambda. Okay, so that is what this whole story is about here. So this calculation ends up giving us a posterior distribution, right? So what we can do is we can now express the posterior distribution, at least the kernel of the posterior distribution we can express by saying that A star is going to be sum of x plus a, which is what the a was for the prior, right? And b star is going to be b plus n, right? So once we know the sum of the data points, the independent data points, and once we know the sample size, the number of data points, we can, and if we define a particular prior for the gamma distribution with some parameters a and b, we can immediately come up with the posterior distribution for the lambda parameter, because that posterior distribution comes from a gamma, is a gamma distribution with updated parameters, right? So here's the story that I just laid out. A star is a plus sum of x and b star is b plus n, right? Now, once you know this kernel, of course, you can figure out this constant, the normalizing constant, by just integrating this expression such that, you get a 1. And so you just solve for k. So k will be 1 over the whatever the expression is on the left-hand side here, this integral here, right? I'm sorry, there's a mistake here. Actually, this should have been d lambda here, right? This should have been d lambda. I will just fix that after the lecture. Okay, so um, Okay, so what we've done is we've derived the posterior. And notice that this is also a conjugate situation. This is the conjugate case because we have a gamma prior and a gamma posterior, right? Just like we had a beta prior and a beta posterior for the binomial case. For the Poisson case, if we use a gamma prior, and that's why the gamma is so convenient, we can um, get a gamma posterior, okay? So here's a concrete example given some data, right? So suppose we have 5 data points here, right? We're looking at 5 independent data points again, just fictional example with n equal to 5, right? Suppose that the prior that we had chosen was as the one that we had before, a equal to 6, b equal to 2. We can now immediately work out the posterior, which will be a gamma distribution. The posterior is going to be gamma 22, 7. A will be 22 and 7 will be the B parameter updated, right? We started with the 6, 2 with 6, 2 parameters. So 6, A equal to 6, B equal to 2. We end up with A equal to 22 and B equal to 7 given the data. Yeah, so that's pretty straightforward. Nice example of a conjugate case. And we can also work out the mean of the posterior now, the new posterior, right? The new distribution that represents the posterior and the variance, right? It's just a coincidence that this is pi, okay? There's nothing special going on there. Okay, so, right, so what we saw in chapter 2, or at least in my lecture, is 2 examples of conjugate cases, the beta binomial, Poisson gamma, right? And so the next point I want to make, the reason I actually showed you the Poisson gamma is that I can show you a very cool demonstration of how the posterior mean in the Poisson gamma case is a weighted mean of the maximum likelihood estimate and the prior mean. Okay? So what I'm going to demonstrate now is that we can express the posterior mean as a weighted sum. And we're going to proceed weighted sum of the prior mean and of the maximum likelihood estimate of lambda. So let's do the derivation, okay? So remember that the posterior distribution's mean is A star over B star. And we know what A star is. That's A plus sum of X. And B star is N over B. So I've just rewritten the posterior mean in terms of the derivations that we came up with earlier. Now, this posterior mean, we can rewrite it in the following way. And we're going to use the following fact. Okay? So one important thing, one important trick that statisticians use all the time is that whenever you see a sum of X somewhere, what they will do is they will multiply it with N divided by N. And what that will give you is this becomes the sample mean, which is often written as X bar. So N times X bar is the same thing as sum of X, right? This is the common trick in statistics that's used very often. So that's how why I converted this sum of X into NX bar. Everything else is the same here, right? Now, if we divide both the numerator and denominator by B, what we end up with is A over B here. So A over B, and then N X bar divided by B in the numerator. And in the denominator, we end up with N over B plus 1, right? So that's what we get here. And this is very interesting because A over B is the mean of the prior, okay? So we can rewrite this A over B as M to represent the mean of the prior. And here I've just rewritten this as the X bar is weighted by this term. And in the denominator, we have the same term again. So what we are looking at here effectively is that we are looking at a weighted sum here, right? Because if we just put a 1 here, right, m times 1, and separate out the numerators into separate terms, we're going to get m times 1 divided by these two numbers, 1 plus n over b, plus the maximum likelihood estimate weighted by, so multiplied with n over b divided by 1 plus n over b. So this is actually now a weighted sum, and it's weighted by these two weights here. Right, so I could rewrite this in the following way. I could set weight 1 as 1, weight 2 as n over b. And so what I will end up with as is that the posterior mean, that's what we were calculating. Okay, this whole thing is the posterior mean, is actually a sum of the prior mean and the maximum likelihood estimate, but it's a weighted sum, weighted by those two terms. Okay, so what's interesting about equation 41 is that when n goes to infinity, what will happen is that this number, W2, the weight 2, will get very large relative to weight 1, which is the value 1, right? So when this number is approaching infinity, then this term will approach 1, right? This term will approach 1, and this term will get smaller and smaller because this weight is getting larger and larger, right? So this, so eventually, um, the as n approaches infinity, the posterior mean will end up depending almost entirely on the maximum likelihood estimate, because this is going to be down weighted very heavily, and this will become 1, right? So the posterior mean will approach the maximum likelihood estimate, right? So So that also relates to that picture I showed you earlier, where the posterior distribution is actually a compromise between the prior and the likelihood. So what's happening is that the posterior mean will drift towards the maximum likelihood estimate if we get more and more data, right? So that uh, that's an important point, because in general, in Bayesian analysis, as sample size increases, the more data you have, what will happen is that the likelihood will start to dominate in determining the posterior. In determining the posterior mean, in this is true generally as well. It's not just for the Poisson gamma case, right? But the Poisson gamma case, I could show you an analytical derivation which demonstrates this relationship between the prior mean and the maximum likelihood estimate. But this situation holds generally across Bayesian, all Bayesian analyses, right? That as sample size goes up, we will get closer. The posterior will be dependent mostly on the maximum, like on the likelihood. So, and similarly, as n approaches infinity, the posterior variance will approach 0. You can see that here because the posterior variance is a star over b star squared, right? And if we just rewrite it in terms of um, the derivation that we came up with earlier, what you'll see is that the denominator is the square of the numerator as far as n is concerned, right? And so as n approaches infinity, this number is going to get smaller and smaller, right? So the variance is going to get tighter and tighter as you increase sample size, which the variance of the posterior, right? So what that means is that as you increase sample size, your uncertainty about the parameter is going to get smaller and smaller. So you're going to become much more, have a tighter distribution for the posterior of the parameter of interest. And what that practically means is that you um, you have a lot more certainty about the parameter if you have a lot of data. So the practical implication of this, let me just again share my screen. The practical implication of this is going to be that um, if you're looking to find a posterior for the lambda parameter, right, that's your goal in the Poisson gamma case, right? So if you have sparse data, you may end up with a posterior distribution that's very widely spread out, right? But if you if you increase your sample size, so n becomes large, what will happen is that the posterior distribution on your lambda parameter could change and become much tighter. And that gives you a lot more information about the lambda parameter because the range of plausible values that it can now have, given more data, is much narrower. And so you can delimit the range of plausible values given the data that you have. So the role of the amount of data that you um, bring into the analysis is going to have a major impact on, um, in general, not just in the Poisson gamma case. In general, it will have an impact on how much uncertainty you have about the parameter of interest. Right? That will become very important later. Okay, so just to wrap up, we have seen two examples of conjugate cases, right? There are several other such conjugate cases. I can give you a list later on. And one very big insight that we got from the derivation for the Poisson gamma was that the posterior mean is a compromise between the prior mean and the sample mean, right? The maximum likelihood estimate. And as I mentioned just now, when the data are sparse, the prior will dominate in determining uh, the shape of the posterior and the posterior mean, even in the case of the Poisson gamma. And when there's a lot of data, the sample mean will dominate in determining the posterior mean in this Poisson gamma case. And more generally, the likelihood will dominate in determining the posterior, right? So one important implication, one last point that I want to make is that when you have sparse data, one major advantage of the Bayesian approach is that you can use informative priors based on expert knowledge or existing data or previous meta-analyses. And these priors, in the face of sparse data, will then play an important role in determining the posterior, right? There's not much to learn from the data, but you do have prior knowledge about the problem, so you can bring that to bear on your analysis. That's not something that you can do with the frequentist approach, but of course, it is the responsibility of the researcher to make sure that if you're using an informative prior, that prior should be well justified, right? You can't just choose some arbitrary prior that you personally consider informative without any, scientific grounds, and use that in your analysis. That would be an inappropriate thing to do. Of course, I will discuss this with lots of examples later on. Okay, so the next step that we will now take is that these two analyses that I showed you with the beta binomial and Poisson gamma, these are analytical examples we can do on paper, but in realistic data analysis, we won't have these simple conjugate cases. So we will have some likelihood function and we will have dozens of parameters. And just multiplying out the priors with the likelihood is not going to be a feasible task anymore. And so what we're going to do is we're going to switch to using Markov chain Monte Carlo sampling to to get the posterior of the parameters of interest. So we're going to get the joint posterior distribution of all the parameters, regardless of whether there are 5 parameters or 500, right? We're just going to get the joint posterior distribution using Bayes rule, using MCMC sampling. And so the next topic that I will cover is different sampling approaches. This is not in the textbook. We don't discuss sampling at all. So what I did was I will just record a lecture. I will record a lecture on different sampling methods so that at least you have some intuition for what it means to write an MCMC sampler. And you should, of course, know how to write simple, samplers like Gibbs samplers and so on, because there can come a time where you're working on a customized problem and you have to write your own sampler. So you don't have access to, ready-made software like Stan, which provides you with some sampling algorithm. So Stan uses Hamiltonian Monte Carlo. In the old days, People used to use Gibbs sampling. I mean, people still use Gibbs sampling quite a lot. So it's not that it's obsolete or anything like that. But Hamiltonian Monte Carlo instead proceeds very, very fast. So you can do a lot of things with HMC that you would find very hard, very difficult to do with Gibbs sampling. And there are some other, of course, many other methods. Metropolis Hastings is another important method. So I will discuss some of these topics in my next lecture. If you want to read up on and you want to get an accessible introduction to sampling, I like one chapter in the Lambert book. He discusses sampling algorithms, and so that's a good place to start if you want to get a handle on sampling and read an independent, presentation of sampling independent from mine. Another interesting book that I want to recommend for sampling is Scott Lynch. Scott Lynch's Bayesian. I don't know what the book is called. Yeah, here, right? So this book has a very good introduction to sampling as well. So you can find this book, a PDF of this book online for free if you want to get hold of it, or maybe ask me for it, and if you ask me, I can give it to you. Actually, no, I can't give it to you. I don't think it's in the public domain, so I won't give you a copy. But I did buy a copy of this PDF of this book from Springer at one point. So yeah, I misspoke there. I can't give it to you. Right. All right. So so that's it. So the next topic will be sampling algorithms, and that'll be the next lecture.